Okay, the unit squared, as parameterized, or as indicated in the document, goes from 0, 0 to 0, 1 to 1, 1 to 1, 0 back to 0, 0 along straight lines. So how do we parameterize that? For reference, I take this path and call it path 1, this is path 2, this is path 3, and this is path 4. So how do we parameterize path 1? Well, in the preceding video I went over this in more detail, maybe the video before last. That is the video before last, unless I change something. Okay, path 1 is just x equals 0, clearly on this path x equals 0, and y goes from 0 to 1. Well, we're going to let y equal t, and let t go from 0 to 1. Now this is a type of parameterization you should be familiar with by now. Okay, if you aren't, get familiar with it, you're going to need it. Path 2, on path 2, all your y's are equal to 1, x is equal to t, so you go from here to here, as t goes from 0 to 1. Now, I chose to parameterize all 4 paths with t going from 0 to 1 for the expedient reason that I can take the expressions for all my integrals and put them into one integral when I get done, and I don't have to evaluate 4 integrals. And there's going to be some simplification within the expressions that we get if we lump them all into one integral. So, path 3, on path 3, x is equal to 1 everywhere in path 3, so we have x equals 1, and y goes from what? Well, as t goes from 0 to 1, y should go from 1 to 0. Well, if you let y equal 1 minus t, that's exactly what happens. And on this path, y is equal to 0, and x is equal to 1 minus t. Then we have our parameterization just in terms of x of t and y of t functions, and we could come back directly into this form of the integral and move on. But just to be consistent, I'll say we could do the r of t for path 1 is, well, r of t is x of ti plus y of tj. R of t then would be 0i plus tj, okay? On path 2, x is equal to t, so it's ti, y is equal to 1, so it's 1j. On path 3, x is equal to 1, so it's 1i, and y is equal to 1 minus t, so it's 1 minus tj. And path 4 similarly. Our dr on each interval is, or on each path is given as shown here. Our dr when r is equal to tj is just dt times j. And when r is ti plus j, dr is just I dt. If r is I plus 1 minus tj, take the derivative. The only thing that gives us a derivative is negative t, so we have negative j dt, and here we get negative I dt. Those are our drs. Okay, now we want to do the integral of del f dot dr, and we're going to do that in terms of our parameterization. Fortunately now we're not going to have a bunch of sines and cosines, so things are going to be a little more tractable than they were here. Still, we need to express our del f in terms of our parameterization, because it's going to be different on each curve. For example, on the first increment here, our x values are all 0. Okay, so we're going to have e to the x times the cosine of xy. Well, that's going to be e to the 0 times the cosine of 0y. Okay, so that's just going to be what? E to the 0 is 1, cosine of 0 is 1, so we just get 1. Over here, what do we get? Well, y is t, x is 0, so it's e to the 0, but the sine of xy is 0, isn't it? Because x is 0, it's a sine of 0, so this whole thing is 0. So we don't get any contribution at all from the I component here. Our I component is going to be 0, I component of del f. If we let x equal 0, well, our j component is also 0. So our del f function is 0 everywhere from here to here. That's not going to give us much of an integral, is it? Now, we want to look at path 2, where we don't get a lot of zeros. Okay, on path 2, and I've written that out, on path 2, I'll show you, first of all, our y is 1 and our x is equal to t. Okay, now we're not going to get any zeros. So we're going to have e to the x, which will be e to the t. Y is 1, so it's just going to be cosine of x. And here, y is 1. We're going to have an e to the x. We're going to have a sine of xy. Y is equal to 1, just the sine of x, but x is equal to t. So that's just equal to sine t. And on the j component, our x's are going to be t's. Our y's still going to be 1, so we're just going to have a sine of x. So let's see how that looks. Now hopefully you can still see our del f function. Okay, so we're going to get what? E to the x cosine of xy. If y is 1 and x is equal to t, that's going to give us e to the t cosine t. Okay, over here, y is 1, x is t. We're going to get e to the t sine t. And those two are going to give us our I component. Of course, we're going to have the negative sign there. That's not going to be changed. And then here, x is equal to t, so we get t e to the t. And right here we have, where is it? Looks like I didn't write my t down. Unfortunately, that's not surprising. Have to have a t here. Then the other isn't going to matter. Sure, that's not going to matter, but I should have written that down. So it's t e to the t, and then times the sine of xy. Y is 1, sine of x is sine of t. Here we have this. So our del f dot dr is del f dot what? Well, on the second interval, dr is just dt. I dt. So it's del f dot I dt. Now I said that the t I left off here isn't going to matter on this part of the integral. It does matter if you're trying to illustrate what you're doing here, and that's what I am trying to do, so that wasn't real good. But what we get here then is going to be this component, the I component here, times the I component of our dr. And we have no j component in the dr, so we have just 0j to multiply by the coefficient of j here, so we're not going to get anything from this. We're just going to then get this I component times dt. And I believe I've got that right. I won't swear to it. I believe I've got it right. Okay. Now, that integral is going to become the integral over path 2 of del f dot dr. Well, I mean, this isn't an integral. It's not going to become anything. The integral we want to do is the integral of del f dot dr over path 2. We want to see what that is. Well, that's going to be the integral from t equals 0 to 1, because those are our limits on t according to our parameterization. And then it's just going to be this function, because this is our del f dot dr. So here we have it. We do this integral. Now you have stuff about eigenvectors and so forth. Ignore that. I was running short on board space, so I had to kind of use a little bit of board space that was left over on this board, but that's pretty much it.